Welcome to our video on the War of Currents. In this video, we'll dive into one of the most intense and crucial technological rivalries in history, the War of Currents. This battle between direct current DC, championed by Thomas Edison, and alternating current AC, supported by Nikola Tesla and George Westinghouse, wasn't just about electricity. It was about shaping the future of power systems around the world. The outcome of this war not only determined how electricity would be harnessed and distributed, but also influenced the future development of electrical infrastructure. The significance of the War of Currents lies in its far-reaching effects on global industrialization, urban development, and technological innovation. By understanding the key moments of this conflict, we can see how it laid the foundation for the electrical grid that powers cities, industries, and homes today. The War of Currents didn't arise out of nowhere. It was the culmination of years of technological innovation, experimentation, and competition between some of the greatest minds of the 19th century. In the late 1800s, electricity was still in its infancy, and many inventors were working hard to develop practical applications. Thomas Edison was one of the leading figures during this period, making monumental contributions to electrical technology. Edison's greatest early achievement was his invention of the incandescent light bulb in 1879, which revolutionized lighting. This success led Edison to focus on the larger issue of electric power generation. Edison was not just interested in creating lights that could replace gas lamps. He envisioned a future where electricity would be available for homes, factories, and entire cities. To do this, he developed a direct current DC system, which was a relatively straightforward method of delivering electricity. With DC, the current flows in one direction, and the power can be easily controlled. In 1882, Edison built the first central power station in New York City, marking a major milestone in the development of electric power systems. His DC system worked well for short-range applications, like lighting nearby buildings, but it had significant limitations when it came to long-distance transmission. As electricity traveled through the wires, energy was lost due to resistance, meaning that the farther the power needed to go, the less efficient the system became. As a result, Edison's DC system required multiple power stations to be built close to each other to serve different areas, which was inefficient and costly. Despite his success, Edison faced a challenge in scaling his system beyond local applications. He was determined to overcome these limitations and sought solutions to make DC a viable option for large-scale distribution, but this process would prove to be far more difficult than anticipated. In contrast, the emerging figure of Nikola Tesla was working on a completely different solution. Tesla's genius lay in his ability to rethink the entire concept of electrical transmission. Instead of using DC, Tesla developed the idea of alternating current, AC. AC allowed the direction of the electrical current to reverse periodically, which meant it could travel much further, without significant loss of power. This innovation would eventually allow for the widespread transmission of electricity over vast distances, bypassing many of the limitations of DC. Tesla's discoveries in the realm of AC would set the stage for a major technological shift in the electrical industry, and he would become one of the central figures in the War of Currents. The battle between alternating current, AC, and direct current, DC, wasn't just a contest of inventors, but a clash of two distinct philosophies of how to manage electrical power. DC worked by maintaining a steady, one-way flow of electricity through a conductor, making it ideal for applications where a constant and controlled supply was necessary. For example, devices such as batteries, radios, and early telegraphs used DC because it was easy to store and use in small, controlled amounts. DC was simple, reliable, and efficient for short-range applications, but its limitations began to show when it was used for large-scale power distribution. One of the major issues with DC was its inability to travel long distances. When DC electricity moved through wires, the resistance in the wires caused the energy to dissipate, resulting in significant power loss. For this reason, DC systems required multiple local power plants to serve small areas, making them inefficient for widespread use. As cities grew and industrialization spread, the need for a more scalable and efficient power system became evident. On the other hand, alternating current, AC, was based on a completely different principle. Instead of a steady one-way flow, the direction of the current periodically reverses, allowing for a more efficient transfer of energy. AC's primary advantage was that it could travel much longer distances without losing significant power, thanks to its ability to change voltages using transformers. By stepping up the voltage for transmission and stepping it down again for local use, AC could maintain its power over vast distances, making it a much more efficient system for large-scale distribution. This advantage made AC ideal for powering entire cities and industries. The ability to increase and decrease voltages with transformers was a game-changer, opening up the possibility for an interconnected electrical grid that could serve vast areas without the need for numerous localized power stations. This is where Tesla's work with AC, particularly his polyphase systems, made a huge difference. His inventions not only made AC practical, but they also allowed it to surpass DC in terms of efficiency, which was a key factor in winning the war of currents. The battle between Thomas Edison and George Westinghouse, backed by Nikola Tesla, was more than just a technical rivalry. It was a fight for the future of electricity. Edison, a brilliant inventor who had already revolutionized the lighting industry with his DC-powered light bulbs, was unwilling to let his system be overtaken by AC. He invested heavily in defending DC, not just with technical improvements but with a fierce public campaign against AC. Edison wanted to ensure that his direct current system remained the dominant form of electricity distribution. One of Edison's key strategies in the war of currents was to discredit AC as dangerous and unsafe. He used sensational methods to convince the public that alternating current was a lethal technology. Edison conducted public demonstrations in which he electrocuted animals, such as dogs, cows, and even an elephant named Topsy, to show the danger of AC. To further vilify AC, Edison also played a role in the development of the electric chair, which used AC for executions, linking AC in the public mind to death and horror. On the other side, George Westinghouse, an industrial magnate, believed in the potential of alternating current. Westinghouse had been following Tesla's work closely and understood that AC had the capacity to scale electricity distribution across large areas. In 1888, Westinghouse acquired many of Tesla's patents related to AC, particularly his polyphase induction motor, which made AC a practical and reliable solution for power systems. Westinghouse was determined to challenge Edison's dominance and promote AC as the better alternative. The Niagara Falls Power Project, completed in 1895, marked a pivotal moment in the war of currents. This project was the first large-scale demonstration of the feasibility of alternating current, AC. George Westinghouse and Nikola Tesla were awarded the contract to harness the power of Niagara Falls and transmit it over 20 miles to the city of Buffalo, New York. The project's success was not just a victory for Westinghouse and Tesla, it was the moment when alternating current proved its superiority over direct current in real-world applications. At the time, this was a groundbreaking achievement. The electricity generated at Niagara Falls was transmitted through AC lines to Buffalo, demonstrating that alternating current could be transmitted over long distances with minimal energy loss. This success showed that AC could power large cities and industrial areas, and it confirmed that AC was a viable solution for widespread electricity distribution. The project was an undeniable victory for AC, and it set the stage for future AC-based electrical grids around the world. What made this project even more groundbreaking was the scale and complexity of the endeavor. The plant was equipped with hydroelectric turbines powered by the water from Niagara Falls, which turned mechanical energy into electrical energy. The electricity was then transmitted through transformers, which boosted the voltage for transmission, and then stepped down once it reached Buffalo. The success of the project was a direct demonstration of the power of AC systems, confirming that they could scale to serve large cities and power industrial areas. The Niagara Falls Power Project was not just a technical triumph, it was a symbolic victory for Tesla and Westinghouse in their ongoing battle with Edison and his DC-based electrical systems. By demonstrating that alternating current could efficiently deliver power over long distances, the Niagara Project effectively proved that AC was the future of electrical power. This achievement gave Tesla and Westinghouse the recognition they needed to secure future contracts and transform the electrical industry. The success of the Niagara Falls Power Project led to the establishment of numerous other AC-powered plants around the world. In fact, the principles of this system became the foundation of modern electrical grids that are still in use today. The project was so successful that it also influenced the design of future hydroelectric plants, which would become one of the most reliable and sustainable sources of energy for generations to come. With the success of the Niagara Falls Power Project, it became clear that alternating current, AC, had won the war of currents. Direct current, DC, despite its initial promise and Edison's efforts, was not suitable for large-scale, long-distance power distribution. The practical application of AC in the Niagara Falls project and other successful implementations proved that AC was the future of electrical transmission. The victory of AC opened the door for the construction of massive electrical grids that could serve cities, industries, and rural areas alike. AC's triumph was not just technical, it also demonstrated the power of innovation, persistence, and strategic investments. While Edison's DC system continued to be used in small-scale applications like batteries and electronic devices, it was alternating current that became the dominant technology for electrical distribution. AC-powered systems would eventually span the globe, transforming the way electricity was used and making it accessible to millions of people. Tesla and Westinghouse's victory marked the beginning of the modern electrical grid, which continues to shape the world today. The War of Currents is more than just a historical conflict. It's a story of visionaries, fierce competition, and technological revolution. The outcome of the War of Currents has had a profound impact on the development of electrical infrastructure around the world. The ability to efficiently transmit electricity over vast distances allowed for the electrification of entire cities and industrial centers, fueling economic growth and technological progress. The legacy of this battle can be seen in the global electrical grids that power everything from homes and factories to schools and hospitals. Thank you for watching. We hope this video has provided you with a comprehensive understanding of the War of Currents and its profound influence on the development of electrical technology. The War of Currents was not just about which system was better. It was about how innovation and competition shaped the world we live in today. If you enjoyed this video, please like, share, and subscribe for more deep dives into the stories behind history's most impactful technological revolutions.